Okay, this video is going to help you understand how to solve exponential equations using logarithms. You'll notice that on the screen we've got four examples of four exponential equations. Your variable, your x, is up in the exponent. Now the first one in the upper left kind of is a quick demonstration of the easy way to solve when you have equal bases. If 4 to the x is equal to 4 to the 15th power, then basic logic tells us, well, if you're going to have equal bases, they're both base 4, and they're equal to each other, then your two exponents have to be equal, or x basically needs to be equal to 15. That way 4 to the 15th equals 4 to the 15th, and you're all set. Now that same idea can help us over here on the right. If you have a base 3 to the 2x, but you also have a 9 over here on the right, we know that 9 is the same thing as 3 squared. So I'm really just changing 9 into something else it's equal to. It's kind of like the substitution, only without a variable. Well, if 3 to the 2x equals 3 squared, then 2x has to equal 2. Your two exponents, just like we said over here at the left, have to be equal to each other. So if I divide by 2, then x equals 1. See if you can use that same idea to solve the two equations at the bottom. Go ahead and pause the video now and try getting equal bases. Think about how 125 relates to 5 and how 8 and 4 can be related. Okay, hopefully you noticed that 125 is 5 to the third, and since the left side of our equation has a base 5, that 5 to the third would be very helpful. Therefore, I can say 5 to the 2x plus 1 equals 5 to the third. Well, get rid of those bases, and 2x plus 1 equals 3. If I subtract 1, it becomes a 2, and x again just happens that if I divide by 2, we come out equal to 1. Again, you can always take that 1, plug it back into the original, and check your answer. But it really does work. Now over here at the right, you'll notice that 2 to the second was what 4 was equal to. The problem is 4 to a power doesn't go to 8 very nicely, but 2 squared becomes 4, and 2 to the third becomes 8, so I can just change both sides. Power to a power tells us that 2 times 5x is 10x, 3 times negative 6 is negative 18, so 10x will be equal to negative 18. And if I divide by 10, well, 18 divided by 10 is really the same thing as 9/5. And there is my answer there. Now that same idea can be used even if you can't make equal bases. The big idea of the logic behind what we're doing is that in order to cancel equal bases, base 4s, remember that logarithms and exponentials are inverses of one another. So if we wanted to say the log base 4 of 4 to the x equals the log base 4 of 4 to the 15th, remember the big idea is log base 4 of 4 cancels. And it happens on both sides. Because those equal bases are on both sides, you end up with your two exponents, or x and 15. X equals 15 down here. And again, that's the same idea that worked to cancel the 3's over here. If we did a log base 3, we'd get 2x equals 2. Lower left, log base 5. And on the lower right, a log base 2. We're using that logarithm to cancel the exponential. That comes in more handy when you have problems such as the ones over here. 2 to the x equals 7. Well, 2 to a nice power, nice even number, maybe some sort of an integer, isn't going to come out to 7. We're going to have to use something in between. Note that 2 squared equals 4, but 2 to the third is already 8. We skipped right over 7. So what we're going to want to do is use a logarithm to find that decimal, find something between a second power and a third power that'll give us 7. So since I need to cancel a base 2, I'm going to use a log base 2 of 2 to the x. So take a log base 2 of 7 over here on the right. Again, log base 2 of 2 cancels away. You end up with just x on the left. And if we can find a log base 2 of 7, depending on what kind of calculator you have, you could use a change of base formula. Change this into natural log of 7 divided by natural log of 2. Or if you have a calculator where you can type in a log base 2, type that straight into your calculator, such as on a TI Nspire. We can just type in logarithm control 10 to the x, so as we get that log base 2 of 7, and we get a nice answer of 2.807. So I can go back to our main screen and say that our answer is 2.807, approximately accurate to 3 decimal places. And again, feel free to plug that back into your formula. Go back on your calculator and say, well, 2 to the power of 2.807. It should come out very, very close to 7. Okay. Note that that is just below 7 because we used the rounded number. Or if you still got the number on your screen, remember you can always go up and copy paste. If I press enter there, and if you put all those decimal places in, we'll end up with that nice solid 7, just telling us that we typed that in correctly. Now, some of these other equations have a few extra parts going on, but go ahead and try using a log base to cancel those equations. Pause the video now, try these 3, and I'll solve them for you here in just a second. Okay, over here on the right, you'll notice that the first thing I did was subtracted 3. Again, do the easy steps first. Easiest thing to get rid of that, or on that side with the x on it, is that 3. Subtracting 3 gives you 22. Then I had a 5 basing on my exponent, 5 to the x plus 2. So if you take a log base 5 of 5, on this side it's going to cancel, leaving you with just x plus 2. On the right side, log base 5 of 22 is a number that you can go find. Realize that if you type that straight into the calculator, log base 5 of 22 is essentially equal to 1.921, approximately. So then the last step is to subtract a 2. Oops, this should be a 2 right here. Subtracting 2. Log base 5 of 22, or our 1.921, minus 2, getting that x by itself, leaves you with a negative 0.079. Along those same lines, down here at the left, I divided by 40. First thing, it's again a big number outside of the exponent, easy to get rid of. Leaves me with 6. Then in order to get rid of a base e, remember I need to use a log base e, which is a natural log. Natural log of e cancels away. I get 0.6x on the left. And again, natural log of 6 is just a number that you can find. If I take that natural log of 6 and divide by 0.6, my final answer will come out to about 2.986, rounded again accurately to 3 decimal places. And finally, over here on the right, you've got 8 to the 2x equals 16. So again, using a log base 8 of 8 cancels, leaving you with just 2x. On the right, log base 8 of 16 is actually 4/3. If I divide by 2, that's 4/6, which basically means my answer is 2/3. Again, you can always take that, plug it back into your calculator, make sure that 8 to the 2 times 2/3 actually comes out to 16. Now, looking at that last problem, you might have also noticed that 8 and 16 hopefully make bells and whistles go off in your brain here. Something's up there. 8 and 16 seem kind of related. So we're going to take a second and actually a third look at this same equation. You could have, such as we did on the first screen, actually also looked at this problem and said that 8 is 2 to the third is equal to 16 is actually 2 to the fourth. So 2 to the 6x equals 2 to the fourth, which means using those equal bases again, equal bases equal to each other, 6x must have been equal to 4, and x equals 4/6 or 2/3. Now, you'll also realize, notice at the top of the screen, the directions here say use a natural log to solve. Even though we're base 8, the biggest idea we need to do is get that x out of the exponent. So another opportunity would be, if I just am looking to get that x out, we need to just take any kind of logarithm. So I'm going to take a natural log on the left side here, and a natural log on the right side. Realize that again, the property of logarithms that we know is you can take any exponent that's inside of a logarithm and move it to the outside. So this can become 2x. Right? I'm going to move that outside. times the log of 8, natural log of 8, equals natural log of 16. Just like we can divide by a 2 to get that x by itself, realize that natural log of 8 is really just a number as well. So I can divide both sides, not only by 2, but by natural log of 8. Again, as long as I do both sides, that's perfectly legal algebra there. And now the 2's are going to cancel, natural log of 8's are going to cancel, and that leaves you with just an x on the left. And the natural log of 16 divided by 2 times the natural log of 8, you'll actually find out will also come out to 2/3. So another great way to solve that problem. Lots of different opportunities, lots of different ways to solve. You can use a logarithm, such as a natural log. You can use a log base 8, like we did on the first screen. Or you can use equal bases when the opportunity presents itself. Now, the last thing I have for you is just an example of one place that we might be able to use logarithms to help us out. Newton's law of cooling is a way of finding how long it's going to take, t, little t here, in order for some sort of liquid, some sort of a stew or a soup or just water to cool near to room temperature. Okay? Well, given the information up top here, take a second to read through it. But then we're going to fill in the different parts of our equation. Realize that the final temperature, which you'll notice in our stew, we're hoping to be 100 degrees Fahrenheit, is over here at the left. So I'm going to say 100 equals. T sub 0 is the original temperature. So the original temperature of the stew is 212 degrees. Well, T sub R is the room temperature. So room temperature is 70 right now. E to the negative, note e to a negative number, so we're doing an exponential decay problem. Our temperature is going down. I'm going to put my rate of decay, negative rate of decay, times T, and then plus the room temperature again over here at the end. Take a few seconds to think through, now that we've got the problem set up, how can we use the idea of logarithms to help us solve this equation? Okay, I've got most of it solved here for you. First thing I did was subtracted 70. Again, easiest move, just get rid of that stuff that's outside the exponent. Notice that 212 minus 70 became 142. So I divided that away next. Then I've got e to the power, and remember we want to get that exponent out of the that variable out of the exponent. So the best thing to do is to take a logarithm that'll cancel base e. Remember, the natural log cancels base e. So once that's gone, once we've gotten rid of that log base e of e, I now have the natural log of 30 over 142. And the last thing I need to do is just divide away my 0.046. So divide that left side by negative 0.046. And t will come out approximately equal to 33.796 796 here. And notice that our rate is degrees per minute. Since we were finding time, that means we're operating in minutes. So a great way to use, again, a natural log or some kind of a logarithm to cancel an exponential. Hope that helps you solve logarithmic equations. Good luck on your homework and have a great day.